just, I don't have my drink. All right. Hi, everyone. Sorry about that. There was some kind of an alarm, and unfortunately, they're going to be running, they just came in then and told me then that they're running some check alarm at some point soon. We don't have to evacuate, but at some point we might be interrupted by an alarm that goes off in the rest of the building. Okay, so we'll see. Now that might be good. It might help wake us up, right? Keep us alert. I don't know. I don't know when it will be. And I've got a strong startle response, so I might be adding to it by, being in shock. All right, let's get started. Sorry for everyone at home as well, waiting for us to start. All right. Shh. Yeah, we did get feedback saying that it's really noisy in the lecture hall. Now, the alarms that will be going off today, I can't stop, but please don't talk in here. If you do have to talk, if something happens, just run outside, talk, shut the door though, and come back in and shut the door. All right. Shh. So there were 2 recordings I released instead of the lecture for Monday because it was a public holiday. I hope everyone had a good long weekend. Maybe everyone was busy working on their uni work, I don't know. The first one is a video with sort of a larger array program, like a 2D array of structs with a player moving around, just to help people get started on assignment 1. So I don't know if you've watched it or not, but there's that. Part 2 is a strings recap, and we looked at arrays of strings and command line arguments, which is sort of new stuff, and multi-file programs, which is new stuff as well. So I know right now everybody's kind of focused on the assignment, which I completely understand, but that's content at some point. If you haven't watched it, you should watch. Okay, and again, if you're focusing on your assignment right now, that's fine, but if you need to talk about it, again, just go so, the people at home or on the recording, everyone can hear. So just please try not to talk. Shh. Okay, good. Don't forget, there's still time to do a catch-up lab tutorial. So there are some labs and tutorials on today. So if you are usually in a Monday tutorial lab class and you missed it and you haven't done a catch-up, look here to see if any of these times work for you. There's some right after this and some later tonight. Oh, I don't have anything on. Okay. Oh. Thank you for telling me that. All right, let's try this again. All right, usually I'm doing the opposite, putting it on when it's not set up, sharing my own emails or something. All right. So there are some classes that you can catch up with tonight. So if that's you missed your Monday Tutor Lab, you haven't been to one, look at one of these time slots and see if you can go. All right? And you can book here. If you've got any questions or problems, just ask us on the forum or on the break. All right, so next week there are no lectures or tutes or labs for anything because it's flex week. But you may not be having a luxurious holiday escape because you will have your assignment 1 to do and also lab 5, right? That'll be due when you get back. There are also help sessions and revision sessions. Shh, please. We're running behind, so just make sure you're quiet. So unless you're telling me the screen's not on, you can speak for that one. So there are help sessions and revision sessions. So this is the part of the course where people are starting, some people or maybe lots of people are starting to feel quite overwhelmed with, the content from this course and, juggling all your other courses. So if you're really feeling overwhelmed and you're having trouble, you don't even know where to begin with things, please do talk to your tutor and let them know, and we can try and work out a plan for you, right? as well as attending help sessions and revision sessions. But if you're even more overwhelmed than that, let us know. We can try and get you back on track and help you, okay? So don't just be silently suffering too much. All right. So today we're going to do pointers. Now, who's heard of pointers before? Who's heard good things about pointers? Yeah, nobody's put their hand up. Oh, what John did. Oh, the admins are telling you, putting their hands up saying there's light at the end of the tunnel. So yeah, people sort of say that typically pointers are a bit hard when you first learn them. That's true. They're challenging, but like anything, once you use them more, you'll get used to them. And anything you do more becomes easier. All right, so we're going to talk about those today. And I'm going to go straight into it. I'm not going to do a recap because I don't think everybody's watched the stuff I'd be recapping. So, all right, let's talk about memory. So we've talked a little bit about memory already, but memory, or like RAM, it's just like, oh, 1 second. A bit disorganized. All right, it's just like a big array of bytes. So memory is just like a big array of bytes where we can store data. And bytes are just, 8 bits, but it's just a big array where we can store data. And we've got memory addresses. Memory addresses are kind of like an index into this array of bytes. So does anyone know what hexadecimal is? Yeah? What? Base 16. Someone said that. I don't even know where that came from, but yes, that's correct. I also, in the drama of today, forgot the chocolate. So, after Flex Week, come up and say, I owe you a chocolate, and I'll give you one. So hexadecimal is base 16. Now, you're going to learn about that in all its glory and gory detail in COMP1511. But basically, when we get up to 9, we don't have any more digits usually when we're in decimal because we've got base 10. But in hexadecimal, once we get to 9, it's just a test. We don't have to do anything except try and live through the noise.
Emergency. Evacuate now. 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 Emergency.
How's this long?
Evacuate now. Emergency. Evacuate now. Emergency.
Okay, I didn't know it was going to go for this long.
Evacuate now. Emergency. Evacuate now. Emergency. Evacuate now. Emergency.
If anyone,
Evacuate now.
if you feel like you need to get away from the noise,
Emergency. Evacuate now. 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 Emergency. Evacuate now.
John,
Emergency.
do one of you want to check how long this is going to go for?
Emergency. Evacuate now.
chaotic and not everyone's back in the room maybe, I'm just going to do a quick Kahoot now, just while it's all still chaotic, and then we'll get into pointers. So let's just do this to sort of get organised again and get back on track. I hope I'm doing the right Kahoot, honestly. It's one of those days. Because there's chaos, we're just going to do a quick Kahoot. All right. Okay, let's, I'll just get started I'll give you one more minute to join. All right. Is anyone still trying to join? I'll just give you another minute to join. Okay, let's start. No, let's not have noise. There's enough of the noise. Very well done. So if we've got a 4 by 5 array, we've got 4 rows with 5 columns, 20 elements. Yep. Can we have more dimensions in our array? Yes. But we don't have to in this course, sort of, maybe. All right. Okay. So array, oops, that color's not good. This is index 0, like this is row 0 here. Row 1, they're just not drawn, in the same way. Row 2. So we're going to row 1, and then within that, we're going to index, 2. So we've got row 1, index 2. Okay, because remember, 0, 1, 2, 0, 1, 2. Okay, the rest of them are on strings, I believe. Very good. Okay, what's it called? Null terminator, awesome. I'm trying to be motivational. What? Yes. So it's I space CAN exclamation mark. So that is 6 characters. If you didn't get 6, maybe you miscounted, or maybe you included the null terminator. That's not part of the string length. That's not part of what the person is actually trying to store. And of course, the quotes aren't in it either. All right. Aha. Yeah, so this one is tricky. What do we call this? Does anyone know? We call it the empty string. So there's not a space in there, it's just 2 quotes together. So it's a string with no characters stored in it, but how big would the array have to be? Yeah. Oh, that's not a good colour. It'd still, at least the array would be 1, size 1 to store that null terminator. So it still is a string, but it's not storing anything that we can print out. And we do use these. All right. So yeah, there's 2 things wrong with it actually. You can't do this, right? This is like making one array equal to the other. What could you do? If you put quotes around the S, then you'd get the string with S in it. Or you could just redefine potato again. But if you wanted to just, yeah? Stop. So down here, where we're checking if they're equals equals, here we'd use string compare. Right? You can't just say, is this string equal to another? It's not going to compile. You'd use string compare. And if string compare returns 0, so I'd say string compare, compare these 2 strings. If it's equal to 0, because string compare will return 0 to say there's no differences, then they're equal. So when you try and do your C code, this is not going to work. With this, you'd have to copy the elements over. Like if you were making a copy of an array, you'd need to do some sort of loop to copy them over 1 by 1, or you could use a string.h library function such as string copy, right, that can copy it for you, or stir copy. All right, you'd use string functions or a loop to put 1 character in at a time. Okay. Okay, social llama. Okay, yep. So I talked about this in the second pre-recorded video, arrays of strings. Yeah, everyone just be quiet because this is important. Arrays of strings. So basically it's like having, in this case, we've got 3 rows, but on each row we've got a string. So cats like a row, dogs a row, birds a row. So each string is a row. Each character within the string is a column. And we can have a max basically of 4 characters in these strings plus the null terminator. So all these strings have to be stored in, 5 spots. We can think of this as an array of strings when we want to. We can think of it as a 2-dimensional array of characters when we want to. In this case, we want to treat them as just whole strings. So really we just go, this is string 0, string 1, string 2. If we print the one at index 1, we just get that whole row or whole string and we get dog. Okay? Does that make sense? We can just think of this like an array of integers and go to the one at index 1, but we get a whole string. Does that make sense? Okay. And yeah, there's more about that in that video, part 2. All right. Okay, so well done, a lot of people got it. Again, we can either think of this as an array of a 1-dimensional array of strings or a 2-dimensional array of characters. In this case, shush, we're going to index 2, and then within that, we're going to index 3. So we get D for bird. Okay? And again, don't worry, that's something new. And if you didn't watch that video, then you've never seen it before. All right. There's no chocolates. I owe you chocolates if you won. So yeah, after Flex Week, come up and ask me for your chocolates. Hands up. Okay. Cool. All right. Thanks, everybody. All right. Everybody quickly say what you have to say. 30 seconds, and then we'll start. Okay, we're going to start now. So, hexadecimal, I was saying, once you get through all your digits from 0 to 9, you start using A, B, C, D, E, F. So you're going to see numbers that don't look like numbers because they've got hexadecimal digits which use A to F. So A's 10, B's 11, C's 12, up to F is 15. You don't have to know how to interpret these numbers exactly, but when you see them, yeah, they're numbers and they're addresses. Now, on our system, our addresses are 8 bytes. So if we print out addresses, which we will do today, I'll show you how to do that, they're going to be quite long addresses. On the slides, I've just made up fake addresses. We don't know what the addresses of our variables are going to be, so I've made just some up for illustration. They wouldn't be this small. They're going to look a lot bigger. All right, so here, imagine we've got memory, and I've got it here in chunks of 4 bytes, and I've just got addresses here. All right, this is going to be in a few pictures. So when we're running our program, once our program's executing, the variables are stored in memory, and memory's RAM, right? Each variable is going to be stored at a particular address. So in this example where I'm just making up addresses, I've got int x equals 1. So there's a chunk of memory set aside that's big enough to store an int in memory that is just there for x, right? And throughout our program, we can use the name x to refer to this value, but it's going to have an address, and this is the address that I've made up for this example. OX just means hexadecimal, by the way, so the address is FF48, and the value that we're storing is 1, right? So if you just try and print out the value of x, you're going to print out 1, but it happens to live at some address that the system knows about. Now, even if we, increment this variable or something like that, it still lives in the same address, right? I've said x is 1, then I've said x plus plus, x is now 2. It's still in the same address. It hasn't moved anywhere. We've just changed the contents. Okay. Now, can we find out in our program what the addresses of our variables are? Yes. We can use the address of operator. So if I've got my variable, in this example, I've just set x to 2. I can say ampersand x, and that's going to give me the address. And now in this example, the address is going to be, in my pretend example, FF48. When we print it out, when we're printing out an address, we use %p, which we haven't seen before. Question?
I'm a bit confused about the hexadecimal on the right. What does it really represent?
It's just a number, and it's an address. So this is a little bit like, homes. Every home has an address, and if you know the address, you'll be able to go to that location and, I don't know, visit the person that lives there. Yep.
So how do we know what hexadecimal we think we're accessing?
Well, you don't, generally, the question is, how do we know what hexadecimal thing we're accessing? Generally speaking, we might never need to care about these memory addresses. We might never need to know. We just call it x. We say x equals 2, and then later on we've got the value 2. Now that we're going deeper into things, we're going to be doing things where we need to do things with addresses. So right now, it's just the concept, and I'll just show you how we can find the addresses when we're running our program. But most of the time, we don't really care about what the real address is. Maybe if we're debugging something tricky, we might print it out. But here, I'm just printing it out for illustration. Generally, as you're programming, you're just going to call it x for the most part. Yeah, question?
Does that mean we've already been using addresses for scanf?
Yeah, that was going to be my next question. If I had a chocolate, I'd give you a few chocolates. Yes, we've already been using addresses for scanf, right? We've already seen this ampersand. So we've been using addresses the whole time. We just said, don't worry, we're not going to explain why you're doing this, just do it, right? That's kind of what we've been saying. Yeah, here's where we explain it. And you might wish we weren't explaining it. But it gives us the address. So we've been passing the address of our variables into scanf. And why have we been doing that? Well, we're telling scanf the address of our variable so it can go and put the data inside there. So it's a bit like if I order a pizza, I give them my address so it can come and deliver the pizza. Here we're giving scanf the address of the variable so it can go and kind of deliver that thing it read in from the user. Okay, there was a question over there. Yep.
So then, can we replace, since we know points now, we don't really have to use, structs, for example?
Someone just said now that we know pointers, we don't have to use structs. Maybe there's some scenarios where you could use, I think what, you might be doing the assignment right now, and you might be thinking, I want to return more than one thing from my function, or modify variables in my function, and maybe the only way you know how to do it at the moment is to use a struct, and then, yeah, this could replace that. But in general, it doesn't replace structs overall. Yeah. And I'll show you an example of that too. So, all right. And Yeah, after Flex Week, we'll be doing lots of examples where we've got addresses of structs and stuff like that. Okay, so let me just show you this. I'll show you in a minute. My VLabs, I'll have to restart it. So we can find out our addresses of our variables, but can we store them in variables themselves? Can I have a variable that stores an address? And yeah, we can, right? So just like in real life, we might store addresses in our phone or something, so we can go and find an address when we need it. We might have variables that store addresses. And they're called pointers. So a pointer is just a variable that can store an address in it. Okay? A memory address. So when we're declaring a pointer variable, as always, we've got to make up a name, which, you know, a really nice name for our variable. Okay, this is just an example name. And then we give the type. So for pointers, we have to give the type that it's actually pointing to. Like, what's the address of? Is this going to be the address of an integer that I'm storing in here? Is it going to be the address of a double? Is it going to be the address of whatever? And then I put this little star asterisk thing, and this is when you look and think, oh, it's a pointer. So here, I'm asking for a variable that I want to use to store addresses of ints. So I can store an address of an int in here. Here I'm asking for a variable I can store an address of a double value in. Here I'm asking for an address I can store, I'm asking for, oh goodness, a variable I can store the address of a char in. Here, a variable I could store the address of a struct person in, whatever that struct person is. So I can have a pointer to anything, but they've all got their specific types. Okay. So how do I give a pointer a value? So I can't just hard code some value because I have no idea where my variables are going to live in memory and the layout that's being used. And I haven't memorized all of those hexadecimal numbers anyway, even if I could do that. So this is typically how we do it. We've usually got some variable. So imagine I've got x, and x is just a normal integer variable. And in this case, it's got the value 2 in it. All right? Everyone's happy up to there, I hope. Now we've got another variable, which, you know, I've given it a great name again, x pointer. X pointer is going to have the address of x in it. So let's pretend the address of x, I mean, we don't really know, is 98, right? Let's just pretend that's the address of x. What we're storing, we're saying, give me the address of x, and I'm putting it in this variable here. So this variable actually stores the address of x. So if you go to this pointer and look at the value, it's going to tell you where x lives in memory. And we call it a pointer because it's like it points to this variable. It sort of shows us the way or tells us where it is. Okay? And at this stage, you might be thinking, who cares? Why do we need it? We'll get to that. But first, we need you to understand what they are. Over here, we've got the same thing, but we've got a double variable. We've got y with 1.5. I've got this thing I've called real pointer. Real pointer. And at the moment, I've just declared it, like with any variable, if you've just declared it, it's uninitialized. Right now it's uninitialized. Now I'm initializing it and saying, let's put the address of y in there. And sometimes, instead of making up fake addresses, we just kind of put an arrow to indicate it's got the address of y in there. All right? Or sometimes I just remind myself and put that in there so I remember if I'm drawing it So often, once you're dealing with pointers, you will be drawing these boxes and trying to visualize what's pointing to what, especially at the start. Yeah, question? Can a pointer point to its own address? Yeah. It can. Whether you want to do that or why you'd want to do that's another question. Or what would happen if you accidentally did that is another question too. But not for now. Good question though. Yep.
Why do we use a star when we're declaring, but we don't use it when we're normally using the pointer?
We haven't shown you how to even use the pointer yet. So at this point, oh, I see what you mean. We're declaring the pointer. This is part of the type, right? Then down here, we're just using, like I would say, usually int x equals 5, and then later I might say x equals 10. You know, I'm not putting the type in. So in this context here, it's like part of when we're declaring the type. Unfortunately, the star is used in a slightly different context as well, but we'll get to that now. But here we're just saying, okay, put this value in here. This is my variable name, put this value in there. Okay. All right, so here, look, I'm just going through the same thing. I've got x is equal to 2, and I've got my beautiful fake addresses over here. I've got y equal to 99. And then I'm making a pointer variable, and I'm putting the value of the address of x in here. So this is just basically what I just showed you before. So the address of x is FF48. X pointer is a variable that contains that address. And we think of it as pointing to that value. And we can say it references x or it points to x. That's the kind of thing we say. Yep.
We can't name a variable with an asterisk in front of it without it being a pointer.
Well, yeah, if you put that asterisk in front of it, and it's going to be a pointer. Like even if there's a space between it, if you're declaring a variable, putting that star is going to make it a pointer. And without it, it's just going to, in this case, be an int. Yeah. All right. Now, what can we do with these pointers once we have them? Well, if I've got a pointer to something, I can dereference it. Now, dereference means basically go to that address and get the value, or go to that address and modify the value. So here, x pointer has the address FF48. When I use this star in this different context, if I say star x pointer, it's saying actually go to this address. When I go to that address, I get 2. So this is going to print out 2. Does that make sense? This is very important. So x pointer equals this address. Star x pointer means go to that address and get the value in this case. And we're printing it out and it's 2. Okay? So, you know, when it's like if the pizza delivery man, he's got an address in his phone of where he's got to take the pizza, but there's no good, you know, he's not going to just drop the pizza there. He's got to go to that address and take the pizza to that address. That would be dereferencing the address. Yeah, question?
Why not just use x?
Yeah, so the question is, why don't we just use x? That would be a lot easier. Now, we're going to show you where this is actually useful soon. So it will be useful. It's like because we've used this kind of thing in scanf. Yep.
Like how we use ampersand for the scanf, can we use ampersand here?
Well, we're using ampersand here because we're saying ampersand x, and we're giving that value to a pointer. Okay? Once we've got the pointer, it can go to that address using this star sign, this star character. So this says, what's the address of this variable? And when we're using scanf, that's what we were doing. We were saying, scanf, here's the address. You go and put the data the user typed in, and now you know the address. Here, we've got the address now, and we're going to go to that address. So scanf is probably doing something like this. It's got our address, we've given the address, and it's going to it and putting the data in. Yep.
Can you point towards a variable in a different file?
No, you can't. The question was, can we point towards a variable in a different file? If you've got a multi-file program, and yeah, that you could be able to. We're not going to do stuff like this. You can't just point to a variable in a program that's not running, that's not your own program, that's, you know, yeah. All right, so we can use these pointers. So we accessed the value before, but we could also modify the value. So here, this value in X was 2, but I'm going to that address because I've got the address of X. I'm going to go there because I'm using this dereference operator, and I'm going to put the value 7 in there. Okay, so once I've got the address of something, I can go to that address and modify it. Are there any questions about this? X pointer is a variable that has the address of X. Star X pointer dereferences it. It says, let's go to that address, and we're setting that value to 7. Yep.
So star X pointer acts the same way as we would make X, like, you know, if you're hard coding it and we're using X instead, then because X will be updated, right? So star X pointer is the same thing as X.
So the question was, is star X pointer the same as X? Yeah. In this scenario, saying star X pointer would be the same as saying X equals 7. Yeah. And this is really good news because this allows us to do things like we can pass a pointer into a function, and then the function can just go directly to our variable and change it, which is what we're going to want to do. Yep, question? Can you do arithmetic with pointers? Yes. Well, with pointers, yeah, you can do it. So you could have an address and do a plus. We're not going to do it in this course because there's some subtle details that we don't want to go into. But you can. All right. So just putting it together. I've got a variable. One more go at this. I've got X, it equals 42. I've got a number pointer. I'm just going to call this NP in my drawing. And it's got the address of X in it. I'm not going to make up a fake address. I'm saying star number pointer. Well, this is my number pointer. It has the address of X in it. So star number pointer means I'm going to go to X and get that value out. And that's going to give me 42. Is everyone clear on why star number pointer gives us 42? It's got the address of X. This means go to that address, get the value. I'm then going to add 1, and I'm going to get 43. And then I've just got a variable Z that's now going to have the value 43. But the pattern of use is typically we declare our pointer. We give it the address of some variable that already exists. Then we can access it using the dereference pointer, the dereference operator. We can go and access it indirectly. Yep.
So with pointers, you can access them from anywhere, right?
Well, yeah. If I pass a pointer, and I'll show you in a minute. If we pass can we access things from anywhere? Yeah, sort of. Like if I pass it into a function, I can go and access something from the calling function. But I'm going to show you examples of where we actually use it in a minute. All right, I've sort of talked through all of that. Do you want more examples to check that we... Oh, actually, I do want to show you all this stuff. I have to start VLab again, though. Oops. What am I doing? Okay. So let's just go through some of this stuff. So this, oh, there's a whole lot of output here. Let me just move this. Sorry. Oh, it's probably not much better. All right, let's run it again. So first of all, what do we have happening here? We've got x. I'm going to draw it so I can keep track of it. X is equal to 2, which is good. Now the next thing we're doing is we're just printing out x, and that's giving us 2. So we're all good up to there. Now we're printing out the address of x. I have no idea what the address of x is going to be, and now it's printed it out, and it's this big, horrible, long address. Okay, this is apparently the address of x when we're running the program this time. Next time we run it, it might not put it in that exact same address. But within this running program, that's where x is living. Now, I've now got a pointer variable called x pointer. And again, it's got, I'm just going to put the address of x in here. It's pointing to x. Right? Now, when we go and print out the contents, if I just print the contents of this variable, I'm getting this value here. It's split across 2 lines. And as we can see, that indeed is the same as the address of x, right? So I printed out the address of x. It's, what is it? It's OX 7 blah, 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 E0. I've printed out the contents of the x pointer variable, the contents. It's exactly the same. It's 07, oops, in here. It's 7 dot, 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 E0. They're the same thing. Is everyone convinced of that? Okay. Oh, and what are we doing here? What does ampersand x pointer mean?
The address of x pointer.
Yeah, we're getting the address of x pointer. Do we need it? No, but x pointer is also a variable that's stored somewhere. So it's got its own address. We're not going to use it in this course. We're not going to go too crazy, but it does, it's a variable, it has an address too. But the address we really care about in this example is x. All right. Yeah, so these are what the addresses look like. Now, what am I doing? Now, when I do this line here, I'm not doing well with the screen management today. Yeah, when I do this line here, what is it going to print? Line 26. So we're dereferencing x pointer. X pointer is pointing to x. What's the value in x? 2. So this is going to print 2. So star x pointer means go to the address and get the value out. X pointer is storing an address. It's the address of x. Go to that address and get the value out. It should give us 2. If I save it and recompile it, it should give us 2. Yep. We get the value 2. Is everyone sort of happy with that? All right. Now, here, I'll just move this over a bit. What am I doing here? I'm saying star x pointer equals 99. So when I print this out, after I've done that, I'm going to print x and I'm going to print star x pointer as well. What's that going to print out? Yeah, so this here, remember, I'm just going to put this back to pointer of x. I've got x which is equal to 2. I've got x pointer that has the address of x. If I say star x pointer, it's going to go to that address and it's going to, in this case, set it to be 99. Once it's done that, when I print out x, x is now going to be 99, right? And if I go to star x pointer is pointing to x, so star x pointer will print out the value in x, and we'll also get 99. Okay, who's completely lost about the dereference operator and how we're getting 99 here? Okay. All right, what are we doing down here? Yeah?
So the dereference operator, is it just virtually the same as writing x pointer?
So this is a very good question. Is the dereference operator the same as x pointer? If I print out the value of x pointer, I'm going to get the address of x. It's going to print out OX7FFE8 blah blah blah.
No, but such as in line 22, you had written x pointer and 22. Yeah.
That's the same as printing out the address of x.
Oh, right.
Yep. Anytime we just print out or do something with x pointer, that's the contents. And that's going to give us the address of x. Anytime I say star x pointer, that's going to go to the address that it's storing and do something to the value or the contents. Okay? So when we're doing this, this is like saying x equals 99, right? Here, this is like saying the address of x, in this case, when we've said it. Yes, question? The question was, can you assign your own addresses? No, the program automatically assigns them. Yep. Good question. And we can just find them out like this. And again, typically we don't need to print them out unless we're like debugging or explaining stuff. All right, down here, just in case it's not confusing enough, I'm making another pointer variable. So the new pointer variable is called num pointer, and we're just assigning it to x pointer. So this is like any assignment. When you say something equals something else, if you're allowed to do it, it just copies the contents of one variable into the other variable, right? X equals y, you're just putting the contents that are in y and copying them into x. So here, This is just copying the contents. The contents of X pointer is basically the address of X. So now we're putting this in. We've got 2 pointers that both have the address of X in there. So they're both pointing to X. Does that make sense? It's basically saying, here's a pointer, I'm a new pointer, and I want to point to where that pointer is pointing as well. Yep.
So if you change the value of the x pointer, the num-pointer value also changes?
Very good question. If we change the value of X pointer, does num pointer change? No. So it's a little bit like if I've got int X, oh, let's not use X. If I've got int A equals 10, and then I say int B equals 10, oh, int B equals A, right? I'm going to have A with the value 10 in it. I'm now going to have B with the value 10 in it. Does everyone agree? Now if I go and change A, I don't know, A is going to have minus 77 in it, but B isn't. They're not tied together forever. You've just copied it in at that one instant. And now they're 2 independent things. When A changes, B still has the same thing. This is exactly what we're doing here. It's just that the value that we're copying is an address, which makes it seem more confusing, but it's the same concept. Okay. Does that make sense? Any other questions? All right. All right. A little bit more to go of this, and then we'll just talk about why they're useful. All right. I've now got this pointer as well. This pointer, where's it pointing? Num pointer. It's pointing to X. So if I say star num pointer equals 10, what's that doing? It's like saying X equals 10. Num pointer points to X, it's going to go there and change it to 10. Okay? And if we go and print that out, it's going to show us, yep, whether I'm printing out X, star X pointer, or star num pointer, at the moment they're all the same. Because, whoops, X has 10 in it. X pointer is pointing to X, so star X pointer is going to give us 10. Num pointer is pointing to X, so star num pointer is going to give us 10. And now I've got weird variables hanging around that I forgot about. I'll just get rid of them. Right, so X is 10, star X pointer is 10, star num pointer is 10. All right. One last little thing. I'm now introducing a y variable, a normal y variable, and I'm putting the value 4 in it. And now I'm changing the contents of num pointer, because these pointer variables are variables. They don't always have to point to the same thing the whole time. So num pointer isn't pointing to X anymore. I'm giving it the address of Y. So it's now pointing to Y. Is everyone happy with that, sort of? Num pointer is pointing to Y. So now, if I print out num pointer, it equals 4, right? I mean, star num pointer. If I go to the address of Y, and print out the number, I'm going to get 4. Right? It's pointing somewhere else. All right.
If we change the value of y, then will the pointer change?
Yeah, so that's a really good question. If I change the value of y, will the value of the pointer change? Yes, because let's just try it. I say y equals 99, for example. What I'm doing, I'm changing this 99, changing y to 99. This variable is pointing there. So when you go to that address, now it's going to have the 99 there. So let's just print that out. Okay, they're now both kind of the same thing. All right, here's just a couple of little bits that are a bit different. We can't do something like this. So if I've got a double variable, I can't make my integer pointer point to it. So if I've got an integer pointer, it's not going to let it compile if I try and put the address of a different type in there. Okay, and it's saying incompatible pointer type, blah, blah, blah. So that's pretty straightforward. You can't do that. The other thing is sometimes we don't have an address yet. So sometimes we have a variable and we want to initialize it to something. We're going to get the address later, and we put this special value of null there. Does anyone remember where we've seen null before? Not the null terminator. So not that \0 we put in a string. This is the null that we can assign to a pointer that means nowhere or nothing. So we've typed it into code at some point maybe, or in the slides. fgets. Yeah, so fgets returns null. And in that case, it's returning to say there's no string kind of thing. No more strings. Somebody's pressed Control D. But we're going to start using it sometimes for our pointers to say, no, there was nothing, there's no address. When we do it, I can go and print it out, and I don't know why. Maybe someone else does. It prints out nil. Why does it print nil instead of null? I don't know. If anyone knows and wants to tell me, please do. But if I try and go there, if I try and dereference null, null doesn't exist. So if I try and go to something that doesn't exist, I don't know, it just makes C kind of explode, we crash, you can't do it. And you're going to do this a lot accidentally, I pretty much guarantee. So just get used to this error message. Let me bring it up so you can see it properly. Oh goodness. Have I compiled it though? Runtime error, accessing a value via a null pointer. You're saying, I want to go to null, address null. It's like trying to go to, I don't know, yeah, it doesn't exist. You can't do it. You're going to get a runtime error. All right, so typically, we do stuff like this. We have code that's checking. If this is not equal to null, then we can go to that address. But if it is equal to null, don't go there, you know. That's our intro to pointers. I'll do this example later. I've talked about the null pointer. All right, I'll give you a 10-second break for your brain. All right, who wants to talk about pointers to structs? Okay. What's the time? I'll keep going. We've already lost so much time. Or do we need a 5-minute break? Okay, 5-minute break, 5-minute break. If you can't concentrate, we might as well have a 5-minute break. but just 5 minutes. We're going to start exactly back on time. Back from the break. I hope your brain's going okay. Let's talk about pointers to structs. So hopefully we're comfortable kind of with structs, and we know here I'm declaring a struct variable called P, and I'm setting the X member inside to have 10 in it, the Y member inside to have 9 in it. So a struct is just a chunk of memory where we can put multiple values in there, all related. But we can have pointers to these too, because these are just variables, right? So what I can do is I've got my struct point P. I can then have a variable called whatever I like. I've called it P pointer that points to this struct. So it basically contains the address of P, right? I've got a pointer to a struct. Oh, what have I left out? I've left out this star character. I have to fix that. That's bad. Just so it's less confusing for now. Okay, so I've got a pointer to a struct. Now, this is tricky, but don't worry too much because there's different notation. The first thing we want to do when we've got a pointer, so I've got a pointer. If I want to go to that address and do something, get the value, put a value, what do I do to my pointer? I've got a pointer, I want to go to where it points at. I use star, I dereference it. So if I've got this pointer and I want to go to this thing I'm pointing at, I do star P pointer. And that's going to take me to the whole struct. It's the whole thing I'm pointing at. It takes me to that struct. Then within that, I would need to say .x or .y. So this would be the syntax of saying, let's dereference my pointer, go to the chunk of memory I'm pointing at. Then within that, because it's a struct, there's an X member. I'm going to set that to 10. Do that again, but set the Y member to 9. Now that syntax gets very confusing, difficult to type. And if you don't put those brackets in, the precedence makes it not work. You know that, like, you know how with the order you do operations, like you do multiplication before addition. Well, the way C works, it's going to do this dot before you've done your star, and then it doesn't work. You've got to put the brackets in. Now, because this is messy and it's a really common thing to do, there's an alternate syntax that we want you to use that means exactly this same horrible messy thing. And it's just arrow. So if you've got a pointer to a struct and you want to set or get any of the values, you just use arrow instead of dot. So that's an arrow because it's kind of like a pointer. I've got a pointer to this struct. Instead of setting a value by doing .x, I use arrow x. And that's a lot easier for everybody to read because anyone who's learnt C and pointers knows what that means, and it's easier to type. Does that make sense? So if you've got a pointer to a struct, don't use dot, use arrow to access the fields. And then you don't have to do stars and brackets and dots. Yep, question?
I wanted to say that the week 6 revision session announcement is on.
Oh, there's just a reminder. Yeah, the week 6 revision sessions are coming up. So just keep a lookout for it. There's an announcement on Ed.
Was made 10 minutes ago.
The announcement's just been made. There's revision sessions coming up for week 6. So if you want to book into those, get on it. Any questions about this? Pointer to struct. All right. So what's the point of learning about pointers? What do they allow us to do? We're learning all this stuff and it doesn't seem very useful. Let's have a look at this. There's not a pointer in sight here, so don't worry. What's this code going to do? What's it going to print out? I've got two functions, update and swap.
Wouldn't do anything, would it? Because it's a void function, it doesn't actually change the main function. Nothing.
Yeah, so what do people think? So I've got x is equal to 2, y is equal to 5. It's going to print out 2 and 5. Then after update, what are the values of x and y going to be? Yeah, still, yeah, exactly what you said is correct. 2 and 5. Why is that?
Because the values don't change inside the function.
Yeah, so we're passing in copies. So the main's going to have its copy of x and y, but we really just passed in the values 2 and 5. So over here, update will have its own versions of 2 and 5, and it'll be adding 1 to its x, minusing 1 from its y, and then it's very happy with itself. It finishes. Then what happens to those variables?
Cease to exist.
Yeah, once the function finishes, all of the memory for the variables and, you know, parameters for this function will be on the stack, and it will be used again for something else. Those resources aren't needed. The function's over, used for something else. Back over here, we're still printing out 2 and 5. Nothing's changed. The same with swap. Now, forget pointers and functions and stuff. Does everyone understand the code in here? So when we're swapping two variables, so we've got, oh, I should draw this back again. I've got the copy of x and the copy of y in this function. Now, a common mistake people do when they're trying to just swap values or swap variables is that they do something like this. What's wrong with doing this?
Temp is not declared, so it doesn't know what.
Oh, this I mean.
Both values will become the same.
Yeah, so when we're swapping two values, if I just say, okay, x equals y, suddenly I've got 2 5s and I've lost my x. I've written over my x. So when we have, when we swap two numbers, we've got to have an extra variable called, doesn't have to be called temp. So I put the value of x into here, and I've got it stored. So then I can put the value of 5 into here. Then I can put the value of 2, which I had stored in temp. At the end, we don't really care what's in temp, but now we've swapped the variables. But nonetheless, once we've done that, this function finishes, and you know, we've still got our variables that are the same. So basically, the slides just sort of show you what I've spoken about. But I want to talk about, has anyone heard the word stack? So in the memory, there's different parts of memory. Let's just talk about this briefly. When you compile your program, you get an executable file filled with like machine code, noughts and ones. That data actually gets stored in memory too. Your actual instructions saying, you know, add 1 to x, that's the noughts and ones that represent that code gets loaded into RAM, and that's in the code section. We've then got a section for global variables and other things. We've told you not to use global variables, so this section for us isn't too important. We've got the heap. The heap will become very important after Flex Week. But so far we haven't used the heap, so we'll talk about it then. But the stack, this is the section that we've been using. This is what stores local variables. So all the variables we've been using. Every time a function gets called, it gets a chunk of memory on the stack, which we call a frame. A frame, and I've got it written somewhere. And it contains the local variables for that function, as well as other information. Because when we're calling functions, we'll be running through the main, and then we'll be jumping off to some function and executing that, and then we've got to jump back to where we're up to. And we might have functions calling functions, and we've got to keep jumping back to these places. These addresses that we jump back to, so we know where to continue in our code, they're called return addresses. So that's also stored in the stack. So every little function will have information telling it, oh, well, when you've finished, you've got to go back to that other line of code. And all sorts of other information is in the stack. And as we know, when the function finishes, actually we mightn't know it in these terms, but it gets popped off the stack. All that data for that function, including the local variables, gets popped off the stack, and then it can be used for something else. Okay, so let's run through the same thing I just did, just quickly with these beautiful drawings. So when we start our main, actually I've just got update here, I don't have swap as well. I start my main function, and it gets a stack frame, a chunk of memory on this stack just for the main function. And as it's running, it gets to, update its variables and do what it needs to do. It's just set x to 2, y to 5. Now it's calling the update function. The update function now gets a chunk of memory on the stack. Again, we call this a frame. There's now 2 frames on the stack, 1 for each function. The frame is just each function's own little area. And it was already passed in copies of the values 2 and 5. So that data is within the update function for it to kind of use. So now when we're doing x equals x plus 1 in update, we can see it's updating its copy down in here. The 1 back in the local variables of the stack is unchanged. We modify y. Again, we're doing the local copies that are in update. As soon as update finishes, that gets popped off the stack, and all that sort of stuff is gone. And it's jumped back to where it was up to in the main. So it used some data stored in the stack that I didn't really draw in there that told it where to go back to. Then, as we know, 2 and 5 get printed. And now when the main finishes, when we do this return 0, that gets popped off the stack too. And then, of course, our program, that's it for us. It's done. So this is what's happening with the stack. And this is happening automatically. The system is making room on the stack for our local variables and popping them off the stack when our functions are finished. We don't get to control the stack. That's controlled for us. All right. We've still got time. Just one special note. Basically, everything's copied into functions. All our parameters are kind of copied. We get copies of our ints, doubles, structs, enums, chars when we pass them into functions. One exception that might be a bit confusing is arrays, and we're going to talk about those later. We can modify those from within a function, right? Has everybody modified arrays from another function? Because it turns out, we'll discuss it later, when we pass an array into a function, we're not passing a whole copy of it. What can you guess that we might be passing? Yeah, the address. We pass, when we just pass the array in, it's automatically basically passing in the address of the array for us. Then the function can go directly to that address and modify it. I'll talk about it in more detail later. But let's go back to normal, let's go back to sort of normal integer type variables. Can we do something like we do with scanf and pass addresses of our variables into functions so our functions can then modify them? And yeah, that's exactly what we're going to do. We'll pass in the addresses of our integers or structs or whatever into functions. The functions can then go to those addresses and change things. So let's go back to this code and try and do that. So the first change is, instead of passing in x and y, which would just give us 2 and 5, we're passing in the addresses of them. So down here in our update function, we've now got the address of this variable up here. We've now got the address of this variable up here, okay? That's what we've passed in. So now, because we've got the address, we can go to those addresses. We can say, well, let's go to this address. So I've got this address stored in my x variable. We're talking about this x variable. I'm going to go there and get the value out, and that's going to be 2. So I get 2 plus 1, which is 3. And then I'm going to dereference this again, go up to here, and set it to 3. I'm going to do the same here. I've got a variable in my function called y. I'll call these x and y. Inside that, I've got the address of this variable up here. I'm going to get that value out, and I'm going to get 5 minus 1 is 4. I'm going to go to that address up here and set that value to 5. Okay, so I'm being given the addresses. I can go straight to the memory locations and modify the data in there. Okay, does that kind of make some sense? So this is one of the most important things that we get from these pointers. Okay, we can go to the address and make a change rather than just get a copy. Okay. Does that make sense? Does anyone have any questions about that? Let's try to do it. Oh, so here's the picture again. We've already got x. We've already got the frame for main. That's the same. It's got x is 2 and y is equal to 5. But instead of passing in just copies of 2 and 5, we're passing in pointers. So down here, we've got a pointer to the x from the main function. Down here, we've got a pointer to the y in the main function. So now when we do this line here, we're going to our variable x. It's got an address. We're going to that address, and we're modifying the value. Here, y is 5, but we have the address of this y up here, and we go there, and we modify it, and now it's 4. Okay. All right, we do have time for this. Yep, question?
Yeah, what if we didn't use the pointer for our update function?
If we don't use the pointer for our update function, then we're just passing in copies of values and we can't modify them. Okay, so I'll show you with and without. Okay, so actually I'll show you with and without now. So here we don't have any pointers, but we're calling this update function okay, we started off with 2, 5. We call the update function. Back here in the main, we still have 2, 5. We call the swap function. It's updating its local variables, but it's not able to modify these ones back here in the main. These just remain 2, 5 for the whole time. Once I start using pointers, now I haven't fixed swap, just update. Now I'm passing in, what's this called? Int pointer. Oh. Okay, we can see that I was able to change something. So update was passed pointers to these, or the addresses of them, sorry. It was passed addresses. It could go to those addresses and update the value, and we get 3, 4. Swap still isn't done like that, so it doesn't work. So if I fixed swap, if I said, okay, swap's going to take in pointers, I pass the address of my x and y into that function. So our pointers in the function will have the x and y addresses in them. But if I just do that, this is not going to compile, right? Because x is a pointer. So if I want to go and get the value out of a pointer, what do I do? So ampersand gives me an address. How do I actually go to the address of something and get the value? Dereference, yep. So for x, I have to go to that address and get the value out, and I'm putting that in temp. Temp's a normal integer variable. I don't put any stars with temp. But to get the value from y, that's a pointer. I've got to go to that address, get the value of y. X is a pointer. I've got to go to that address to set that value. Y is a pointer. I've got to go to that address to set the value. Temp is not a pointer. No, I can't put a star there. So that's where you'll trip up as well. You'll come here and you'll probably just think, I don't know, and put stars everywhere. Maybe. Maybe that was just me when I was learning. Let's just see if it works. Yeah, so we can see each time they're changing from within the function because we've got pointers. So really that's the main point. And I'm not even trying to do those bad jokes on purpose. They're just coming out of my mouth. That's the point of all this, to be able to do things like this. We didn't really get through as much as I'd planned today. That's okay. When we come back after Flex Week, we'll revise these core concepts and do all the stuff we didn't do today. Have a great break. Get help from help sessions. Maybe not much point asking for feedback today.
I'm trying to do this, but like save one, this key and this pointer, serve as a pointer, and then I just why cannot print out this DCC status?
So you can't do dot.